let's start talking about resistors in parallel circuits. So this is when each resistor is connected directly to the power source or the voltage source by connecting wires that have negligible resistance. And each resistor has full voltage of the source, I should say source, applied to it. Okay, so I'll have to look at that in a minute. But here is another thing that each draws the same current it would if it were alone connected to the voltage source, meaning that each current will be different along these parallel resistors. Okay, so let me get a different color out and start looking at these diagrams. So A is what we're going to be looking more deeply into. B is just a example of what you would see in a house. So houses will have many parallel circuits, because if we have everything in series, like the light bulbs were in that, and like the Christmas lights or holiday lights in series, if one bulb goes out, the whole string is going to go out. So we don't want that in a house to happen, right? If one of our bulbs go out, we don't want the entire house to be not lit anymore or working with anything. So what they do is they create a lot of parallel circuits throughout the house. That way, if one thing goes off, that's not a huge deal. Just replace that bulb and you're good. It's not that the whole thing is going to go out. Okay, so let's talk about this in what we will see. And we'll talk a little bit more about, there's certain laws or rules, sorry, that will help us to determine these values exactly. But let's look at this generally for a minute. So in this case, we have our voltage source, okay? We have a positive and a negative, and we have a current in each of these little loops, okay? So this current I is going to have a current here with our first resistor. Then we have another current here with the second resistor, and a third current that goes through here with our third resistor, okay? So each of these currents are separate, and they depend on the resistance that it's going through here. And so our total current I is going to equal the sum of each of those currents. Okay, so it's going to be current 1, 2, and 3 added up to equal our overall current. Okay, so this is again in parallel. Remember that in series, that was not the case. Okay, all right, so this is our current, and then because of that, our due to some details that I'm leaving out, our overall resistance is going to be equal to 1 over P. So, I'm sorry, R sub P. So this, let me get white out here. Let's erase this guy. Okay. This R sub P here, that is our total resistance in parallel. That's what the little p is for, okay, parallel. So the inverse of that value is equal to 1 over R1 plus 1 over R2 plus etc. Okay. And again, this is due to some details that I left out, but feel free to look at them in the textbook. But this is all because the voltage remains the same throughout. So our voltage at R1, R2, and R3 are all equal to each other, okay? Again, look back at the resistors in series if this kind of sounds familiar, but it's it's a little different. Okay, so again, in series, the voltage changed, right? In the series, this voltage stays the same throughout. Okay, so it's kind of like our voltages and currents kind of swapped. Okay, anyway, if that confused you, just ignore that. Let's just look at our current here. So again, current, they add up to equal our overall current. Voltage stays exactly the same throughout, and our resistance, we will actually have 1 over our resistance is equal to the addition of each of the inverses. Okay, all right, so let's look at an example. This would probably help. Okay, so let's look at our first example here. So we're looking at that same figure, and I can redraw it. We had voltage here. Okay, so that's R1. Then we have R2. Oops, I missed the resistor there. Looking at 3 resistors in parallel. R3. Okay, positive, negative, and that's our voltage. Okay, so we're looking at the exact same idea as the first example we looked at, as in the values are all the same. So we are going to be able to compare them and see how they differ. Okay, so let's first look at the total resistance, A. So what is our total resistance? So remember that our total resistance is 1 over R in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3, since we have 3 resistors. Okay, so there's a couple different ways you can do this. I like to plug it straight into my calculator pretty quickly. So I'm going to do that. So we've got 1 over our first resistance, which is 1 ohm, plus 1 over our second resistor, 6 ohm, and 1 over our third, which is 13 ohm. Okay, so the textbook has you solve these individually right now. What I would rather do is plug this whole thing into my calculator. And it seems a little tricky, but really it's just fractions that you're plugging in and adding together. Okay, so this is what I'm going to do. I'm going to say RP, and then in my calculator, I'm going to type all of this. Okay, so be careful with your parentheses. Remember to put parentheses around each one. Okay, this will be the easiest way to do this, in my opinion. If you find out a different way to do it, feel free. But this is how I'm going to do it. So I'm going to say 1 over 1, which is just 1. 1 divided by 6 plus 1 divided by 13. Okay, so I'm going to get some decimal number. So that would be 1.24. And my ohms, my units, are on the bottom. Okay, and that's fine because we still need to flip it, right? So now we need to multiply this by each side, or what we can do is take the inverse on each side. I think that's the easiest thing, especially when you're plugging it into your calculator. So our overall resistance in parallel circuit is equal to, and all you're going to do is take that answer that you got, and you can do 1 divided by that number. That would give you the inverse, or you can do the caret symbol to the -1. It is up to you. So this is the value I got, and I can double check that that's correct. by doing it a couple of different ways, and yes. So this is my resistance, and when I inverse this, the units go up top. So now I have it in ohms, which is perfect. That's what I'm looking for. So this is my overall resistance of this parallel circuit. Okay. All right. So that is the first part. Now the second part, I'm looking for the total current. So remember that the current here is going to be the addition of each current. Okay. So it'll be I is equal to I1 plus I2 plus I3. And we don't have those currents readily available, so we will have to solve for them. So remember that V is equal to I times R, or I is equal to, divide over the R, V over R. Okay. And our voltage, remember that our voltage stays the same. So V stays the same. So V is equal to, I guess you can just say constant throughout parallel circuit. Okay. All right. So this will be V over R1 plus V over R2 plus V over R3. Okay, so you can plug this in individually, however you want to do it. So we can go, V is 12 volts. We could also pull out our voltage if we wanted to. So it would just be voltage is equal to, voltage times 1 over R1 plus 1 over R2 plus 1 over R3. I'll just show you what that looks like. Since the voltage stays the same, we can do this. However you want to do it is just fine. So let's see, I is equal to our voltage, 12 volts, and that'll be multiplied by 1 over 1 ohm plus 1 over 6 ohms plus 1 over 13 ohms. Okay, so we'll have 1 plus 1 over 6 plus 1 over 13, and then multiply that by 12, and we get a current, our total current of 14.9 amps. You can also do this stepwise. You can solve for each of these individually and then add them up. That works too. Okay. I just did it a little bit of a quicker way, but if breaking it down into each step makes more sense for you, that's totally fine. Okay, so this is my total current. Oh, I just did part C. Part C asks calculate the currents in each resistor and show that these add to equal the total current of the source. So I actually just did part C kind of. Just because I solved for each of them sort of individually, even though it was at the same time. Okay, I think it was wanting me to use, let's see, V equals IR. It was wanting me to use that. I just did it in a more complicated way at first. So each of my currents, I1, I2, I3, I can just solve for those really quick. So this is 12 over 1, so that's 12 amps. I2 would be 12, whoops, over 6. which is 2 amps. I3 is 12 over 13, which is 0.9 amps. So adding those up is our total current here. So let's go ahead and check to make sure that that is the same as if we calculated it this way. So I'm just going to squeeze that in up here just so that we're all on the same page. So V is equal to IR, or I is equal to our voltage over our resistance. So our voltage is again 12 volts. And our resistance is what we solved for in part A, okay? That is this 0.804 ohms. So let's try that. 12 divided by 0.804, and lo and behold, we get 14.9. 14.9, and this is in amps. So that checks out. Okay, so I kind of did that backwards, sorry about that. But either way you do it, obviously, it looks like it will be the same value. Okay. All right, so this next part, we will be calculating the power dissipated by each resistor. And yet again, we are using another formula. Power is equal to voltage squared divided by resistance. So I'll go ahead and start to do that. So part D, V squared over R. All right. So P1 is going to be 12 volts over R, which is 1 ohm. Okay, so 12 squared is just 144, and this is in watts. Okay, P2 is going to be 12 volts squared over our resistance, which was 6 ohms, and that gives me 24 watts. P3, again 12 volts squared divided by 13 ohms, and I get 11.1 watts approximately. Okay, so let me go back here. So that is by each resistor. Okay, so I found that. Then I want to find the total power output of the source. Okay, so I'm going to use P is equal to I times V to find that. So we found our current in the last one. We found that to be 14.9 volts. No, amps. What are you doing? Sorry about that. Okay. Amps. And then voltage again is 12 volts. That's not changing. Let me double check our current. Perfect. So we have 14.9 times 12. That gives me 178.8 watts approximately. And then the second part of this question is making sure that this would equal the sum of the other three. So let's see, P equals P1 plus P2 plus P3. And then instead of writing those all over, I'm just going to go ahead and do that in my calculator. So 144 plus 24 plus 11.1 approximately, we have and 79.1 watts. And as you can see, they are very close. They are about 179 watts, so that checks out. Okay. All right, so just summing all the things up that we just looked at for parallel resistors, okay? That is found, the parallel resistance is found from this equation here. Remember, it's the inverses, and it's smaller than any individual resistance in the combination, okay? Each resistor in parallel has the same full voltage of the source applied to it, okay? Um, and parallel resistors do not get the total current, they divide it, okay? So they, again, it's not equally dividing, but it will portion it up, just like in the series with the voltage, okay? All right, so I'm going to stop here, and then we'll continue with combinations of these circuits.